Here we go. All right, so you should be on 13.6. I'm going to run you through the top of it to develop the equation for a capacitor based on the geometry. In other words, you get two metal plates. How much capacitance does it have? They're just sitting there laying around. What is it I'm interested in? Okay, so what determines how much it would be? So logically, you might think things like, well, okay, if I have two metal plates and they're big, the capacitance would go up. Why? Because there's a lot of places for electrons to hide. So I'd expect area to make the capacitance bigger. The distance between them might be a little bit more interesting because there has to be a distance between them because you don't want the charge leaching. But the closer they are, the more they're going to be drawn, more the electrons on one plate are going to drive electrons off the other plate, correct? So does the distance being smaller might increase the capacitance, right? The closer you can be. There's a limit to that. You don't want them too close to each other, otherwise you've got electrons jumping the gap and you don't have a capacitor anymore. You just have a really bad wire. But there's a way to derive this from scratch, and we should do that. The answer is on the formula sheet. So at the end of the day, I'm running you through something just to see how this works. And ... Not all capacitors are two plates pointed across each other. You could build a capacitor by putting a ball with a wire attached to it and a sphere around it. Just because we're physics students, we might come up with something bizarre like that as a capacitor. Then you'd still have to be able to solve for the capacitance of this particular spherical arrangement. So I'm going to walk you through how to find it for two parallel plates. And then as part of the work you're going to do on later problems, you're going to end up doing it with, let's say, a ball and a sphere, or a cylinder and a cylinder wrapped around it, which would also create a place where charges would be attracted or repelled from each other by the gap in between them. All right, so here we go. We're going to play the little game here. I've got, so the first thing it says is we've got, you take two metal plates, place them in parallel to each other. It'd be good if I could draw them in parallel, but not. I got a wire coming to the back side. I got a wire coming to the back side of this one. So there's an air gap between them, so their charge can't jump across. Electrons start to pile up on one. What happens is they want to get away from other electrons, so they spread out along that first plate. And then on the other side, the electrons flee, revealing a positive set of charges there. Agreed? Okay. And that creates a potential difference, right? Because electrons want to go from this plate down to this plate here. They can't do so because the air gap is sufficient to keep them from going across if it's a properly made one. The more the charge, the more the potential difference. So we know this charge goes up, the voltage of this, the desire to jump across there is going to go up. And so we might say something like, as the voltage goes up, my charge goes up, and I need some sort of a constant, so I'm going to put a C there. Oh, C is our old friend capacitance, and this is where this thing comes from. Capacitance is a coulomb per volt, which again we're going to call a Faraday or a farad. Okay. Now, what is the electric field caused by a single charged plate? Oh, well, we're going back a whole chapter, right? So if we go back a whole chapter, we would recognize that that would be, oh, okay, so back a chapter, the charge from a plate would be, oh, I got to use a little Gauss here. So I got the EA, I'm not going to write the formal version of this, it's charge enclosed over E naught. And if I take one of the two plates, and I have a charge distribution over it, let's say positive, just to make my life a little bit easier. I'm going to put a cylinder, I'm going to punch a cylinder through it. Okay, so my charge enclosed would be a circle on that plate. I'm also going to assume that I have a hat boy, which is my charge per unit area across the plate. And generally speaking, they're going to spread out, especially on a metal plate, because it's a conductor. They're not going to sit next to each other, so therefore this is going to be uniform throughout, so I don't have to worry about anything weird like that. So you're just using a little bit there. I go E. The Gaussian shape I draw, only Gauss lines are going to go through the two end caps, and so I would go, that's going to be 2 times pi r squared y2, because I have one on the bottom, one on the top, and flux line would go through both of those. And that's going to equal charge enclosed, which I don't have a formula for, so I'm going to use hat boy times the area I chopped out of this thing, right? Hat boy being my charge per unit area, times the area I chopped out to make it my charge enclosed, and I got over E naught. Now again, all this should be review, but it might not be. And that area of that circle, by the way, is going to be pi r squared. These pi r squared are the same, so they cancel out. And so like we got in last chapter, the electric field formula for a single plate is going to be hat boy, again, charge per unit area over E naught. So therefore, what's the electric field caused by 2? So we know how much this one pushes this one. This is also going to pull the other way. So they're going to add to each other. And so it's going to be double this. Well, it's already a half, so the electric field caused by 2 plates would invariably be a hat boy over E naught. Okay, so the potential difference is, oh, how do I find potential difference? Well, it's just electric field. We remember that between 2 charged plates, the electric field lines are going to be straight as an arrow because electric field is going to be the same. They're going to be equally spaced out. So therefore, I technically should go to find my voltage. I should do, where's my pen? There's my pen. There's my pen coming back this way so I can find it. Okay, so I should technically go the derivative of the electric field with respect to distance is equal to voltage. But I remember, well, duh, voltage, my integral, that was really bad. My integral of electric field with respect to R is equal to my voltage, okay? But since electric field's a constant, this is just going to be E times the distance, and so that's equal to voltage, agreed? And so by swinging back over here, I recognize that I got hat boy over E naught is equal to my voltage. Agreed? The hat boy is my charge per unit area. So I'm going to bring that down. I'm going to say charge per unit area times E naught is equal to my voltage. And then I remember what I've got up here. I've got Q equals CV. So if I move, okay, wait a second, I messed something up. So let's back up. I dropped my D along the way. That's not great. Hat boy over E naught's my electric field, right? So I still need a D here. And so, okay. And so, hat boy over E naught, times D. Okay, so then I still have a D sitting here, right? And so I want to leave Q by itself. So I move everything to the other side. I get VA over D. And is my E naught on top or bottom? My E naught would be on top. Agreed? All right. And so this should be my expression for Q equals V A E naught. Well, this part here, not counting my V, has to be my capacitance based on this formula we have right here, right? So therefore, my capacitance formula is going to be A E naught over D. Agreed? And that actually works for an air-filled capacitor or a normal capacitor with 2 metal plates on it, and that's not a problem. That said, that's not the end of the story. All right, so we had capacitance down to the area of the plate times E naught over the distance between them. We already talked about why this would be the case. It's not really that shocking. The bigger the plates are, the more charge you can store for the same amount of voltage. The closer they are together, the smaller the distance, the more that's going to go up, as you're going to be attracted to each other to the limit where you've got electrons arcing across because you're actually making a wire, not actually a capacitor. So that's cool. Works beautifully, but what if I can make it stronger? How would I make it stronger? Here's what I would do. I would take the 2 plates and I would fill the gap between them with goo. Now, this goo has to have 2 properties in order for it to work. The goo must be polar. In other words, it has to have a positive side and a negative side and some ability to move. Not massively, we don't want it to be floating around or anything, but we want it to be able to turn, so that the positive is approaching the negative and the negative is approaching the positive. This increases the effective charge, right? Because it puts negatives closer to my positive plate and puts positives closer to my negative plate, which strengthens the effect and drags more electrons to this plate, which throws more electrons off of this plate. In addition to that, it can't be conductive. If it's conductive, this thing is going to shut down because electrons are just going to flow through the goo. Such materials are called dielectrics. Dielectrics can flip, but they don't transmit charge. They're non-conductive. Okay? Now, we are physicists. We're lazy. So what we did is we said we're going to call something the dielectric constant. What's the dielectric constant? The dielectric constant is how much stronger my capacitor is because I'm using this dielectric goo in between the two. So all I have to do to my original equation is say, well, here's what a capacitor would normally be. I'm going to make it 4.9 times more powerful because I'm using Bakelite. And I put the Bakelite glue in the middle, and the Bakelite glue holds it, spins the charges around, and makes it 4.9 times stronger than if it was just filled with air or space, actually. All right? And so if I just want to figure out how strong a capacitor is, I simply now use this formula to find the strength of a capacitor. All right? Okay, with that in mind, I'm going to pause this. I'm going to upload this video, and then I'm going to ask you to go ahead and try problem number 1. It should not be that hard. So do problem number 1, and I will show you the correct answer in just a moment. All right.